numbers 28, 29. Yeah, has to do with that. So this is where we're getting into this. It's called a quantum mechanical model. This is kind of the bridge over from this. Okay, we're going to go up beyond the base. He starts leading us into it. All right, what we're going to do is we're going to pick an element. And the element I'm going to pick is sodium. Sodium is atomic number 11, and its usual mass is 23. So I want to draw a Bohr model of this, which would mean how many protons would it have? It would have 11 protons. And good markers we got there. Who's that nice purple one? 11 that is a good one. 11 protons. Okay. And it would have how many neutrons?
12.
12 neutrons in its nucleus. All right. How many electrons would it have? 11. And how would they be arranged? The first energy level would have 2,
8, 1.
then 8, then 1 electrons. Okay? Alright, so now we have the basic subatomic particles in this. We have protons, we have neutrons, we have electrons. Out of the 3 subatomic particles, which of them is by far the most important to defining sodium and its characteristics? Electrons are, by far. If you really get down to it, chemistry, for the most part, is a science and study of electrons. Alright? Now, if electrons are more important than protons and neutrons, except when you're studying nuclear chemistry, in which case you're studying the nucleus, okay, and what happens there, most chemistry has to do with the electrons and what goes on there. Okay? So if we're talking about the electrons, which electron or electrons out of all of them in any given atom are by far the most important? The valence ones in the outermost shell. So we can even go further and say the vast majority of chemistry is really the study of valence electrons. Right?
Yep.
Okay? So what we're going to do is we're going to focus on this guy out here. Electron number 11, out there in the 3rd energy level. Okay, this one just has 1, that's why I picked it. Right? Now, is that electron that's in that 3rd energy level, as pictured there, is it just sitting still?
No.
No. We have a little model of it drawn here, just sitting still. What's it doing? Moving. And according to Bohr, it'd be moving in kind of a planet-like orbit, right? Zipping around. How fast would it be going?
Very, very fast.
How fast?
150,000 miles.
Faster. At or about the speed of light. It can be affected by being in a charged field. Okay, you can't really speed them up beyond that as far as we know, but you can slow them down a little bit. Okay? So at or about, so it's moving ridiculously fast. Alright? Now, it is in the 3rd, what do these things represent? The shells or energy levels. How many energy levels are there for the 100 plus elements that exist to arrange themselves into? The answer is sitting right there in front of you on the periodic table. How many? 7. Where are you getting that, which is right. Where are you getting that number 7 from? These numbers here, right? These are called period numbers. They represent the energy levels. So there are 7 periods. So I'm going to put, I know I've got a drawer over some of this, so I'm going to put the 4th energy level, the 5th, the 6th will be out here somewhere, the 7th. Now if we go back to Rutherford's model, would this really be to scale?
No.
Nucleus, energy levels, well, where would that 7th energy level be?
Southport.
Well, probably if it were going that direction, yeah, Wyndham or Sebago Lake or something, right? With a lot of what in between?
Space.
Empty space in between. All right. But actually, that's not entirely true with the 7 energy levels. Because when you get right down to it, the more you learn about this stuff, the weirder it gets. There aren't just 7 energy levels for electrons to exist in. There's actually, they're at an infinite amount of energy levels. Okay, for them to fit into. There are an infinite amount of energy levels for electrons to fit into. So they can go on forever and ever and ever. Okay? But we're going to focus on this electron right now. Right now, this electron is in its normal position. Granted, moving fast, but it's in its normal position. Alright? There's a name. When we're talking about this in chemistry, and mark it where it's decent, there is a name for this normal position electron. even know what it is. And it's no, it's not normal position. All right. What?
Stable.
I really don't want to watch this.
Base.
No.
It's standing point.
Gravity. Shot football.
What? What?
Rounded.
What?
Rounded.
Close. You had it right first time. Round. You're right. Normal position is called the ground state. So here's our first kind of term today. Ground state position for an electron is where it normally exists. Again, so that one electron's ground state is in the third energy level. These 8 are in the second energy level. These 2 are in the first energy level. That's where they normally exist. Okay? Now we can get that electron to move from this energy level out one more energy level if we add more energy there to the system. Okay? We add more energy, we can get it to move. So I can get it to leave here, and we can get it to move out here to this position. Okay? That amount of energy, so this is going to be our added energy here. There's a name for it. This is a Q term that we come across. It's called a quantum of energy. This is called a quantum of energy. A quantum of energy is a definite amount of energy that's needed for an electron to move from its ground state.
So it's always the same even if it...
No. So that's the other thing. It varies. It varies with the electron's position, which varies, of course, with the element.